So, hi, today I'll be presenting three architectures, the Llama 1 and the Llama 2 paper, and then the Gemma um, architecture by Google. So, let's get started. So, we had the first paper, Llama, come out in Feb 2023. So, it's just hardly a little more than an year old. And we already have, as we all know, like two more variants, Llama 2 and Llama 3. But let's get started and see why this paper is important and what are the new things that they have done, what are their findings. So most of us already know that this paper is by Meta and it had a huge controversy because what they did is that you essentially have to sign basically a sort of an agreement that you will not use this Llama model for any commercial purposes, and then only the model weights were supposed to be provided to the users. And then what happened is after that, some people got the weights, they uploaded it on Tor and other places, and like people started accessing them. So then there was this other controversy that there was this alpaca model which was further fine-tuned from Llama, and they actually made their weights available. So some people started complaining that, oh, Llama is not freely available, but alpaca is, which is sort of a violation. So they eventually had to take it down. So Llama was involved in a lot of fun things, I would say. And when it came out, when it came out, the original Llama 13B model, it claimed to outperform GPT-3 model, which was like 175 billion. So the 13B model is essentially around an approximate like 10 times smaller than the original GPT-3 model, but still the performance was comparable. And then the Llama 65 billion model was shown competitive to the PaLM-540 billion models and the Chinchilla-70B models. What they show, another important point in this paper is that, unlike previous studies, they show that it's actually possible to achieve these, good like comparable state-of-the-art performances, even if you just train on publicly available data. So most of the other data sets, the data set for other models such as PaLM or Chinchilla, those were not all publicly available. A lot of those were proprietary data sets. Llama said that it's actually possible to actually train a state-of-the-art performance LLM if you even just pay attention to whatever public data sets that are there. So before we get started, let's actually look into the data set which was actually used to train Llama. So we have a bunch of data sets. We have the common crawl data set, we have the C4. I know a lot of you will feel that these two are sort of similar. We will discuss them. Then we have the GitHub repositories the data from Wikipedia, books corpus, archive, and Stack Exchange. Here in the next column, you see a sampling proportion. So this basically says that what subset or sample of the entire data set was actually used for training the Llama model. So for example, for common crawl, you say that you only use 67% of the original data set. Then we have the disk size, which is basically the size the data occupies. And then we also have epochs. So what usually happens is that when we are trying to train this data, train a LLM on this data, we'll sort of come up with a data mixture. So this data mixture is actually what is indicated here, that 67% of common crawl is used, 15% of the C4 data set is used, and eventually we'll stop whenever we see some sort of convergence. So at that point, the epochs for which this common crawl data was observed is roughly like 1.1. So this is the epochs column. This is what it shows. If you observe, only the Wikipedia and the books dataset have been trained for more than 2 epochs. For most of the other dataset, it is just 1 epoch or slightly some more steps than after 1 epoch. Overall,
just one question here. So there is also a lot of overlap between the different data sets, right? So common crawl might be containing GitHub and Wikipedia, right? So this is after deduplication that they have done, or this is before that?
So this particular table, I don't know actually whether this was like whether this lists after the deduplication process or before that. But I'm assuming that when they have curated this dataset, they have actually done the deduplication, and only then after that they have reported that of the deduplicated dataset, we use only 67% of this. But this was not specifically mentioned anywhere in the paper. This is just my guess.
So one more question here. So this is 67% of the entire common crawl, or 67% was the percentage of common crawl among all the data
Uh,
sets on which this model has been pre-trained on?
no, this is 67% of the entire common crawl that was deduplicated. So these all won't add up to 100. Or
Acha,
maybe
this will not.
even or
Okay.
maybe even if they did, I mean, even if they did, maybe, I mean, what they're saying is that the entire thing was not used.
Hmm. Okay.
So, and the nice thing about this work is that they list like different types of deduplication techniques that they have used. For example, if we take the English common crawl, they say that, so they take the common crawl dump from say 2017 to 2020, and then there is this CCNet pipeline. What this pipeline basically does is it has a lot of heuristic based rules to actually deduplicate the data. And the interesting thing is this deduplicates at a line level. So this process deduplicates the data at line level. It also performs language identification and basically filters out non-English data. So most of this data is actually in English language. One interesting thing that they did in this CCNet pipeline is that, so they will use a classifier and then they will try to classify some pages whether as they have been used as references in Wikipedia. And they will basically discard pages which have not been used as references in the Wikipedia dataset. So this is the English Common Crawl, uh, like the process for deduplicating the English, like the Common Crawl dataset, which they have used in the Llama dataset. The second one is C4. So C4 is basically just a newer version of the Common Crawl corpus. What they have done is they have curated it for more time and then they have done a lot of pre-processing. In this paper, they mentioned that the main difference with the English Common Crawl, which was like the earlier data set, the main difference is that English Common Crawl uses this heuristic based sort of filtering, and in this particular case, that's not the case. They have like a language, they have different deduplication steps. The exact details were not mentioned, but I'm assuming this is coming from the T5 paper. And they say that CCNet is usually quality filtering, so it relies on heuristics such as punctuation marks or removal, basically based on these types of heuristics. Next, we have the GitHub dataset. So they say that we actually specifically use only those repositories which come under these Apache, BSD, and MIT licenses. And then they say that we deduplicate these datasets at a file level. So if there are two files which have the exact same match of the text or the code, they'll just remove that. So earlier, the other dataset was deduplicated at line level. This was deduplicated at a file level. Then we have the Wikipedia dump. So this is actually a very small data set. So they have curated it from June to August 2022, and they cover 20 languages. Although they do mention that this data set, because like this is a very small data set, like the multilingual aspect is not going to be very strong, even though there are like 20 languages there. Then we have the Gutenberg book corpus. So, the first one is Gutenberg project, which is like a website where you have a lot of books available. Most of these are classics. And then we have the books three corpus, which is books three section, which is again a subset of the file dataset. So what they have done is they have extracted these books from these two datasets, and they say that again here we deduplicate at the book level. So they will only remove books which have more than like 90% of content overlap. So it's possible that some books might be existing in both of the datasets. So that's why this entire book level deduplication was required. Then we also have the archive dataset. So what they say is that they process these archive LaTeX files actually to be added to the dataset. They say that they remove anything which comes before the first section. So I'm assuming this is the introduction. They have not specified any details, but I'm assuming that they'll remove the title and the author information and the abstract information, which sounds a bit I mean, honestly, ideally we should have kept the titles and abstract, but maybe they just decided to do it for some reason which was not mentioned. They also say that they remove the comments from the .text file. So, and similarly things which are mostly like LaTeX logistics, like inline expansion of definitions and macros. Finally, they also use the Stack Exchange data. So Stack Exchange basically has a lot of websites, so it could have Stack Overflow and other things. So they say that they keep the data from 28 largest websites, and then they do a pre-processing where they will remove the HTML tags from the text, and basically the answers, because for each question on the website we could have multiple answers, they will basically sort them by the highest score. Then coming to the tokenizer, so what they have done is they have used a simple byte pair encoding algorithm. One different thing that they say is that all numbers will be split into individual digits. So there won't be any, so if we have a number like 326, it will always be splitted as 3, 2, and 6. There won't be cases like 32 and 6 or 3 and 26. And then one other new thing, this is not essentially a new thing, but this has been adapted in most of the other papers also, as we will see. So they fall back to bytes to decompose unknown UTF-8 characters. Um, we already saw that there are two versions of the dataset. One is a 1 trillion tokens dataset, and the other one is 1.4 trillion tokens dataset. So what they claim is that the Llama 7B and the 13B models, they are trained on 1 trillion tokens, and the 33 and the 65 billion models, they are trained on this entire 1.4 trillion tokens dataset. Then this is just the statistics of different models which have been made available by them. So, for example, we have the smallest model, which is 6.7 million parameters. The hidden dimensions are 4096. We have like 32 layers. And then one interesting thing which I actually never noticed was that the batch size was 4 million. And the number of tokens, again, this denotes the size of the data set on which this was trained.
There is question from Hitesh in the chat.
On the previous slide, what is score in Stack Exchange? Oh, so Stack Exchange is basically like Stack Overflow. So I think what they have there is you'll have some ratings from the user, which will basically denote how many uh, users are basically saying that this is an accepted answer. So I think that is how they have sorted. Does that answer your question?
Shruti, just one question here. So this is byte level byte pair encoding, or this is like the standard byte pair encoding BP?
So I think this is standard byte pair encoding, but what they have done is in case there are some unknown characters, they'll fall back to byte pair, byte level BP.
Okay. Hmm.
Okay, so moving on to next. So the
Yeah,
architecture.
just one more question here, Shruti. So
Hmm.
learning rate they have kept same, or they have changed during the training?
So I don't think this is I actually never thought about this. I have the paper open. Just give me 1 second. I'll just maybe
Hmm.
check quickly. So they say that they use a cosine learning rate scheduler. So they have used cosine learning rate scheduler actually. So it will basically decay after some steps and then again start from whatever the initial values are listed here.
Hmm. Hmm, hmm.
Okay, so this is actually the architecture for the Llama model. Um, Before I actually start discussing how this is different, maybe some of you could have a look at it and try to see how this is actually different from the transformer architecture. Anything significant which maybe any one of you is
Uh,
seeing
y-
here?
yeah, hi. So maybe I was just wondering, is sweet glue? So what is this? Like feed forward sweet glue? Is it like the activation layer, like similar to Galo or?
Right. So this is a different type of activation function which is used in Llama architecture.
Hmm.
Uh, yes. So that is one thing. There are two or three more things.
RMS norms, rotatory position and encoding.
Hmm.
Exactly. So I think, sorry, I don't recognize who that was. Maybe it was
Group.
Amod, but yeah, Dhruv. Okay. So Dhruv has already picked up two things that we
Uh,
have used RMS now. Sorry.
yes, I was actually telling about group multi-layer, multi-query attention.
Oh,
It's
acha,
Amod
acha.
only.
ठीक है, sorry. Okay. So Amod has already picked up like three things. So one is RMS norm, when we have rope embeddings here. And then I think he also mentioned that we have group multi-query attention. I apologize, actually, this is, so in Llama 1 architecture, actually group multi-query attention is not used. This is actually Llama 2's architecture. But yeah, we'll come to these differences. But yeah, most of these are there. And probably the most trivial thing is that this is just a decoder and there are no encoders here. So yeah, so for reference, we have an encoder-decoder type of architecture here. Instead of, say, a layer normalization layer, which is applied after the attention layers here in transformer, what we have is a RMS norm layer. Then instead of ReLU, we have this SWIGLU, which is the new activation function that is used. We have, instead of like these cosine and sine position encodings, we have the rotary position embeddings. And of course, we only have a decoder-only model. So before we move ahead, all these things which we have discussed here actually are not the main contributions of the Llama paper. So this usage of this, what do I say, this instead of layer normalization using this different type of RMS norm is actually proposed by the GPT-3 paper. Basically, it was not exactly proposed, but it was used and shown to be effective there in the GPT-3 paper. So they have adapted it from there. Then we have the SWIGLU activation function, which is coming from the PaLM paper. And then we have rotary embeddings, which were first like, so I mean, these papers were individual papers. So rotary embedding was an entire different paper altogether. But GPT-Neo, for example, was the first paper which actually, like first large scale paper, which actually used these rotary embeddings. Okay, so coming to pre-normalization. So what happens is usually that, okay, maybe we can go back to the architecture here. What we observe here is that this layer normalization layer, this normalization layer is actually applied to the output of each of the units. So it could be either a encoder, decoder attention, self attention, or even after the feed forward network. So this layer is actually applied to the output of this subsequent previous layer. What pre-normalization does is that it says that instead of applying it to the input, we'll actually apply, instead of applying it to the output of a sub-layer, we'll actually apply it to the input. So if you see here, this RMS norm is actually applied before we pass the input to the feed-forward layer, or this is applied before we do the self-attention thing. So that is the pre-normalization part. Now, okay, so a quick question. If everyone is aware of RMS norm, maybe I'll skip the next few slides. Otherwise, I'll just discuss how this is different from layer and batch normalization. Maybe you all can say a yes or no, and based on that, I can decide.
No.
Oh, sorry, I actually forgot what is no for? No for not discussing it, or no for not being aware?
Discussing it, not
Okay,
being
okay,
aware.
okay, okay, thanks. Okay. Okay, so let us start with a very simple feed-forward network. We'll start with what normalization is, why do we need it in the first place, okay? So suppose we all are familiar with this NN dot linear layer, okay? So this basically simulates a feed-forward layer. Now, anyone who wants to guess, if we have this type of like initialization, I mean, not even this, the answer is there on the slide, but if we have this thing, we define that in features is 3 and out features is 5. Would anyone like to tell how many neurons are there in this feed-forward network?
8.
15.
Okay, so there are actually just 5 neurons. What this says is that my input, every input is going to have 3 features, which is the in feature dimension. So if we pass an input of feature 3 dimensions, it will basically give me an output feature of 5 dimensions. So for every input, if I pass a 3-dimensional vector, it will give me a 5-dimensional vector. So there are just 5 neurons. The weight matrix is actually 5 cross 3 or 3 cross 5, as you would call it. So there will be total 15 weights, because each of these features will be given to all of these 5 neurons, and then there will be an output from each of the neurons. So overall neurons are only 5. The weight matrix is 15, as we can see here. Like the weight matrix will eventually have 15 weights. So now suppose we have this example here. So let's say we have an input matrix. So now this is not just a single instance. We have 10 instances in this matrix. So suppose if I'm doing some type of digit classification using a simple feed-forward network, I have like 10 inputs here. And then every input is represented using 3 features. So every input is a 3-dimensional vector. The formula is very simple. We do that X into W transpose plus B is the bias vector. So that the size of the bias is going to be the same as the number of neurons, because we'll add a bias term to each of the neurons, right? And usually there would be a non-linearity which is also applied here, but let's forget it for now, okay? So what will end up is that we do an X with W transpose plus the addition of bias, and then we'll end up with a matrix. So here we started with a 10 cross 3 matrix, which meant that we have 10 instances, each of dimension 3. And we'll end with 10 instances again, which is basically an output for each of the instance. And then we have 5 features. So essentially, this is not a classification, I'm sorry, because in classification, you would have ended up with a 10 cross 1 type of thing. If it was like a single type of classification. Here we are saying, so for example, this is just a simple transformation where we say that we go from 3 features to 5 features. So I hope everyone is clear on the numbers which are presented here.
B should be 10 cross 5, right?
B should be 10 cross 5. No, so this is actually the same bias
Because
vector which...
XW transpose will be 10 5. Okay.
So the thing is that this is the same bias vector which will get added to all the 10 instances.
Okay.
So the way this happens is that this is basically, this B is actually broadcasted to every row after you do this X cross W transpose. Okay. So yeah, you were right that the dimensions don't match, but they don't match because we have to add this bias at every neuron. Okay, so this is telling the same thing, that the bias vector will be broadcasted to every row in the X into the W, X into W transpose table. Okay. Now we have reached till here. Now, as you might have observed, the output of a neuron for a single item or single instance, which is basically coming to it, depends on the input features, right? If you check here, the output, this particular output is basically, we'll do something like this, right? A1 into W11, then A2 into W12, and something like that. So all these actually depend on the input features which are coming to it, okay? Now this actually input is coming from a previous layer. Now when we are doing any sort of gradient descent, if the previous layers, if the weights in the previous layers are updated and they change basically drastically, what will happen is that in this particular layer, the weights will also have to be updated drastically, right? Because whatever is input, based on that, the outputs will have to be adjusted, right? So what happens is that this destabilizes the training. Sometimes it takes very long for this training to actually converge. So this particular phenomena is called internal covariate shift. And we want to avoid it because the more we often this, the training would be slower and basically it would be unstable. So this problem of this jumping of activations, there are like 2 or 3 methods which have been proposed. The first one is batch normalization. The second one is layer normalization, and then we'll also see something which is RMS norm. So one very simple idea to do that is that, so suppose you have these 10 items, and then you have, for every instance, you have these 3 features. What we'll do is we'll compute the mean and the variance. So this is for each row. So for every instance, we'll compute this mean and the variance. What we'll do is we'll normalize this by subtracting the mean and use this formula basically. So here gamma and beta are actually learnable features. We can forget about these, but what we have done is we have subtracted the mean and divided by variance and plus some epsilon. I think this is some sort of error margin or something. Again, this is also a parameter. Okay, so what we have done is we are sort of introducing some sort of rescaling by dividing by the variance root, and also doing some sort of recentering. Recentering is that we are subtracting the mean from the new entry, which we'll get, which is x dash. Okay, so if we are doing this normalization with respect to the batch, okay, so if for first feature we compute the mean and the variance and then do this, we call this batch normalization. If we do this for each row, basically for each of the features, we compute the mean and then we compute the variance for all the features for the single instance. And then we do this normalization. This is called layer normalization. So layer normalization is used in the original transformer architecture. people came up with batch normalization. Batch normalization has some problems, like for example, if there are different sized batches, or it is actually dependent on the batch very much. So people then started using layer normalization. Llama, on the other hand, uses RMS norm. So RMS norm is basically a simpler version of layer normalization if you think about it. So what they say that is, in RMS norm, they say that we only focus on rescaling invariance. So if you look here, the rescaling part is done by division by this variance or root of variance. And the reshifting part is done by subtracting the mean. So they say that instead of subtracting the mean, we'll forget about it and we'll just divide it by the root mean square. Okay. So the formula is very simple. If you have a feature a of I, the new value is basically old value of a of I divided by RMS of the entire vector A into some GI. GI is again a learnable parameter here. So this is similar to what we have here, gamma. So this gamma, this is similar. Similarly, we have here GI. Okay. And the intuition is similar, that they say that we simplify this layer norm by only focusing on rescaling, and we actually ignore the recentering aspect of normalization. The way, I mean, more than this, there is no other intuition.
So intuition wise, it is okay, but like, is it also shown that this performs better than the layer and the batch? Hello, am I audible?
Yes, sir, you are audible, but we
Okay.
are
Yeah.
unable to hear the
So Himanshu, can you once check if Shruti is joining?
Yes, sir. I'm just calling her.
Okay, yeah, sure.
Hello. Hello.
Yes, you are audible.
Oh, I'm so sorry. I don't know when did I get disconnected. Let me share the slides again.
So, Shruti, I was asking this question that has it been shown that RMS norm does better than layer norm and batch norm?
Yes, sir. So the RMS norm paper actually shows that this is better.
Okay.
And
Oh, so
why they
which norm has come before?
So I'm not sure actually about the layer norm and batch norm ka beech ka, I mean, time difference. But
Mhm.
RMS norm is the most recent one.
Oh, so it has come at least after these two, right?
Yes.
Okay.
So
and
did I get
is
disconnected at RMS norm?
yes.
Oh, okay. I did not discuss any of this in the meeting. Rotary position embeddings.
No.
Oh, okay. Okay, let me start from here again.
So in RMS
Uh,
norm, I have one question.
hmm, hmm.
Why they haven't considered recentering? Is there
Why they
any
haven't considered? Sorry, what?
recentering? So they have written we propose RMS norm only focus on rescaling, but not recentering.
Hmm.
So
So I
ignoring the
mean,
recentering aspect.
hmm, hmm. So that's what I'm saying. So what they say is that if you look at the original Basnom or Leonom, they all have this, they both of them have this recentering aspect, which is dividing by the mean. But they, I think, did some experiments where they say that actually this recentering aspect is actually not having any significant difference. And even if we remove this recentering with respect to the mean and just have this rescaling, which is dividing by the variance or root mean square of basically all of the root mean square statistic, this actually performs better or gives you a better performance, even though actually if you look at it, the computation here is less. So we have one less computation, which is subtracting the mean from all the values. Okay, so this is the only explanation that they give, that it is less expensive computationally wise, and it also works well in practice.
Okay.
And actually, they might have some theoretical proofs, but I didn't go into that. So maybe for that, you could refer to the original paper. This is the original paper, Bio Zhang and Rico. You could look into this paper.
Okay. Got it. Thanks.
Okay, so yeah, so I was saying that the second different thing which is used in the Llama paper is rotary positional embeddings. Uh, so okay, yeah, coming here. So what? Um, sorry, I'll just take a few seconds to refocus where I was. Um, okay, so we have in the transformer architecture, we have something which is called an absolute positional encoding. Why is it called absolute? It's called absolute because it's specifically determined by the location of the token in the sentence or whatever is the input. And basically, if you remember in the transformer, like original position encoding, which we have using the sine and cos, we'll have this term I. So every positional encoding that we compute is has just one parameter, which is the parameter I, which is the location of the token in the input. And this positional encoding is like different for different locations in the input. And this is basically added to the token embedding X before we actually start doing anything else. So if you remember, this is actually added at the beginning to the token embedding itself. Now, one drawback of this positional or sorry, this absolute positional encoding is that if you have trained a model for say context length of 1024, so your model would have seen these 1024 length, I mean positional encodings only for only for the maximum index of 1024. So if you somehow want to reuse the model and basically use it for a longer context, the model will get confused, right? Because it has never seen any encoding which is for a index which is greater than 1024. So what the other new technique is, which is saying the relative position representation or relative position embedding. It says that if you have two words which are occurring at the same relative distance, then ideally the semantics is that they are occurring at the same relative position. So we could have a relative position embedding. I'll talk about the details of that, but this is the paper self-attention with relative position representation, which I'll be discussing, which is the relative position embeddings. So, okay. So what they say is that they have a very simple idea. So if you remember the computation of attention in the original transformer paper, we have something like this, right? Let me turn on the pen. Okay. So we have something like Q into K transpose divide by root DK का softmax into then the value वाला matrix हमारा. So again यहाँ पे Q is K into WQ and then K is X into WK and Q is X into WQ. So this matrix, this Q is actually here, X into WQ. Then you have this K transpose, which is X into WK matrix divided by this root. And I've just taken out this term, which I have called EIJ. Okay, so this EIJ is just what you see here. So this EIJ is basically the attention score. This is just a term, but eventually we normalize it by applying softmax, and this could be sort of considered what is the attention score between the ith and the jth token. Okay, so when we apply a softmax, we'll get these probabilities. So this we have already seen, the left half of this slide, we have already seen in the transformer paper. So the related, and mind you, in here, X is actually the token embedding and the positional embedding in the first layer, and after that, this X is actually the output of the previous layers. So this is what we have in the original transformers paper. Relative position encoding say that we'll do something slightly differently here. What we'll do is that X is basically the same token embeddings, but here we'll have these extra terms, which is basically addition of Aij K and Aij V. What this is saying is that we'll have two matrices K and V. These are basically to be added whenever we are doing this operation. So one is for the key matrix, and the second one is for matrix. And this Aij actually denotes the relative position. We are computing the score between the second and the fourth token. This Aij is actually denoting the relative position embedding for the second and the fourth token. So this is just the relative position encoding aspect. So originally, if the equation was this Q into K transpose, we just say that we'll add this additional term which captures the relative position difference. So this is done in both key side also and the value side also. Okay. So in between, all the operations will remain same. So if we have the softmax here, the softmax will remain same as it is. Okay. Okay. Any questions till now?
So I have one question here. So you are doing it at all the self-attention layers or at the first one only?
So this is done at like all all attention layers. And the interesting thing is that this is actually shared across all different heads. So we don't actually initialize these differently for each of the heads. Okay. So now then we have these. So now computing the actual value of this Aij and Aij of V. Okay. So what we have is that we'll say that we'll fix a maximum relative difference first of all. So this maximum relative difference, say for example, could be K. So whenever we have this A2, 1, which is being calculated between the first token and the second token, this will say, let us say for example, this is just a value W minus 1. Then for 2 and 4, this is W2. For 4 and n, this is some K. And K here is the maximum difference which we can have. Okay, so if you have say K as 4, then any relative difference of 5 will actually still be represented as W4. So we won't go beyond some WK. And the reason for doing this is that they say that based on their experiments and ablations in the paper, they say that it's actually not necessary to actually basically going beyond a certain distance, it does not have any additional benefit. So they'll just clip it at some K. And again, we'll have these two differently for the value matrices and for the key matrices. So this Aij and this Aij would be different, but it would be shared actually among the different multiple heads.
So
Okay.
again, these are two different matrices, right?
Yes, these are two different matrices.
Okay.
So again, this Aij for the key matrix, this is defined as W clip of J minus I, comma K. So this K is the maximum maximum relative difference which we have taken, and J minus I. Again, for the value matrix, this is again same. You have a W clip function, and this clip function is basically defined as the difference, and basically you should not exceed the range. So again, this basically translates that for each pair of tokens in the input, when we are computing this attention score, we'll have one of these values in the K matrix, which is like this will range from say minus K to plus K. And again, for the value matrix, we'll have one of these values, which will range from minus K to plus K, because K is the maximum relative difference which we have taken. Overall, uniquely, we'll have like 2K plus 1 values. And again, the formula remains the same, that we'll just add it while we are doing this multiplication. So we'll add it to Aij, this Aij term during the attention itself, while computing the attention itself. Okay, so this was about relative positional embeddings. A similar but a slightly different form, I think, was used in the T5 paper, and also like it was originally proposed in the T5 paper, but it was, I think, slightly different, and they say that this actually performed better than the original absolute positional encodings. After this relative position embeddings, we have this rotary position embeddings. So this paper, I'm apologizing beforehand. So this paper has a lot of math, and I'm just skimming over some of the basic details which I could understand. And yeah, hopefully, if you want to look more and dig deeper into the concept, maybe you can go and read the paper. Okay. So the idea here is that they say that when we have these relative position embeddings, so sometimes, for example, if I have a phrase that the dog is chasing the cat versus the phrase that cat is chasing the dog. So here dog and cat are actually occurring at the same relative difference. And because these two tokens are same and interchanged in these two sentences, the position embedding which we'll get is actually the same. Ideally, so they say that we should have some sort of difference. So here what they have done is they say that we'll start with a very simple idea, that suppose we have two vectors, query and key, and they'll start with describing what is the desired, what is the desired thing that they want. So they say that we want basically some sort of function where, say, if we have a vector x at position m, we should have a function that if we give it xq, which is the query vector for the token x at position m, it should give us this qn, which encodes the position somehow. Similarly, same for keys also. So they say that if you have a token n, and this xk is the key vector for the token x at position m, we want some fk function which will give us this kn function. Which will give us this position aware key vector. And they say that in attention, what we have is we are doing some sort of dot product or inner product. So they say that ideally we want these functions fq and fk such that when we do this q transpose k, so this is done in attention computation, right? So we do this q into k transpose, or maybe the opposite also. What we want is that this should translate into some function, and we are able to find some function g such that we can take just the input embeddings of xn. So this is not the query and the key vectors. This is actually the token embeddings. And then we can just use this G is actually dependent on the relative distance between them. So we want some functions f and q such that this product q transpose k, this can be decomposed such that there is a function G. So this G function exists such that this is dependent on three things. The first is the individual tokens, and then the relative distance. So what we have done is we are basically trying to find a function which satisfies these things. So what will happen is that we don't have to do this individually at every layer. We can just have these two things, which is token embeddings, and pass the relative difference between these two tokens, and then just get this q transpose k directly, compute this directly. Okay. So they say that they define this G function like this F and G functions like this. They say that if you have an FQ is for the queries, FK is for the keys. Okay. So they say that we'll define this function as WQ into XN. So this is again the same X into WQ vector, but they add this additional term, which is e to the power in theta. And then again, for the keys, this function is similar. The G function is defined as this real part of this entire term. Okay. I won't go into the details of all this, but what this basically translates to in 2 dimension, let us look at that. So if you look at this function basically can be written as this FQK, which we come here, this position X of M comma N. So either the query or the key function, this could be translated as this. So if you look at it, this is actually the same thing which we do. So we do this W matrix into X matrix. We just have this new matrix which is added here, basically multiplied here, sorry. And this is the rotation matrix. Now this is only, if you look at it carefully, this is only for 2 directions. So if you have a two dimensions, so if you have 2 dimensions, this type of embedding this function is basically just rotating the original vector in 2D space. So this is very simple. If you have a vector like V0, if you rotate it by some angle theta, this is the matrix which you multiply it with. So V dash would be R theta into V0. So this is what this function is defined as. It is basically rotating the original vector or the token embedding into the W matrix in some 2D dimension. Now, we don't actually have 2-dimensional vectors, right, in real life. So what they say is we'll define a new matrix which can be generalized or basically generalizes our results in 2D to some a higher dimension. Okay. So they say that if you have an X of dimension RD and if D is even, you can divide this D dimension space into D by 2 subspaces. And how they do is that, so you have the matrix, the rotation matrix here, and then you set everything 0. So this is how this matrix looks like. So what will happen is that here they say the main idea is that if you have a token at say first position, you will rotate it by some theta. If you have a token at second position, you will rotate it by 2 theta. Similarly, if you have a vector at some nth position, you will rotate it by some n theta degrees. Now, then there is some technical aspect that if you look at it, this matrix is actually very sparse, right? So when we are doing this computation, when we are computing this, the key and the key and the query matrices from the token embeddings, what we can do is we can actually, instead of doing this entire multiplication, we can basically make it more computationally efficient. What we can do is do this operation instead of actually multiplying all those matrices. So yeah, this is one of the technical aspects which I think was like efficient. So maybe I wanted to cover that. One important thing is again that this is applied to the queries and keys, but not the values. And this rotary position embedding matrix, this is actually applied after we have multiplied the X vector with WQ and WK. So after we do the regular WQ and WK computation, we'll apply this rotary embedding matrix. I know I might not have been super clear while this explanation, but yeah, if you have any doubts, I'll try my best to explain. Okay, moving to the next slide. Okay, so the third different thing which was different in the Llama paper in comparison to the transformers architecture is this SWI-glue activation. So they say that instead of ReLU, we use this SWI-glue. Now this SWI-glue is basically, so in transformers, we'll have a 2-layer feed-forward network, right? So this is ReLU to the output of first layer into second layer basically computation. So this is WX plus B and inside also WX plus B plus this max is the ReLU part. SWI-glue is basically slightly different. So SWI-glue basically says that we again have, we apply the swish function on the input, then do this thing. And yeah, I mean, the only thing is that this formula is different. Funnily, the SWI-glue paper says that we have no explanation like why this works better. They have some funny line which says that they attribute all this success to divine benevolence. But yeah, this is mostly like an empirical thing. They maybe tried some different formulas and it worked better. Okay. So now here, this is a summary of the Llama 1 and the Llama 2 model ka comparison. So what we have seen till now is actually Llama 1. So we have seen differences which were introduced in the Llama 1 paper. And then if you see Llama 2 actually has 2 variants. One is the regular Llama 2 trained version, pre-trained version. And the second is the chat optimized version, which was introduced in Llama 2. The model size actually remained the same. The context length increases from 2K to 4K. Llama 2K bigger models, the 34B and 70B models, they use this PQA, which we'll discuss. Llama 2 is trained on a bigger dataset size, so they instead of 1 and 1.4 tokens, trillion tokens, they have 2T tokens, and again, learning rate I think remains the same.
Shruti,
Okay, so
just one
coming,
question here. See, can you go back to this slide? So it has been trained on this context length, but it can support longer lengths also, right?
I don't think so. I think it was the Llama 3 paper which said that they are supporting to, I think, 128K context length or something.
Okay, but it has been trained on a smaller context length, right?
Llama 3 actually I'm not sure of, and I'm not covering Llama 3 also today.
Okay, fine. So that at least the data sets are publicly available on which the Llama 2 has been trained.
Llama 2 may, I mean, all the datasets which they have already used, those are publicly available, but whatever pre-training and everything that they have done, so they do have a Llama repo, Llama recipes, but
Hmm.
I'm not sure if all the cleaning and pre-processing thing has been publicly available or not. At
Okay.
least, but for Llama, it was available. Llama 2, I am actually not sure.
And what about the scripts, like scripts for pre-training or scripts for fine-tuning, that code base?
I think that is available.
That is
Even the
available.
logs are available.
Okay. Can you share that on that Google form, right? So I'll have a look on it.
Okay.
Sure. Okay, thanks.
Also, Llama also has a long Llama variant, which is not publicly available, which was released after Llama 2 actually and before Llama 3. But they did not release the model and they did not even release the code. They just had the paper. And I think there is Open Llama repository which tried to replicate the long Llama paper. And they did run into some issues, but I think they were sort of able to replicate the paper. So I think for people who are interested in long context models, they could also look into long Llama. And Llama 3, though we already know it has huge context length. I think the base model is 8K or something. I don't remember exactly. And yeah, they are also promising like 128K context lengths. Okay, so coming to the pre-training data. So we already saw like a detailed breakdown of the Llama 1 paper, and they originally say that they have 1.4 T ka tokens dataset. यहाँ पे they have 2 trillion tokens of dataset, and what they say is that they actually use again publicly available sources, but this time they say that they actually use a lot of better pre-processing to actually remove a lot of toxic data. So they say that, for example, sorry, I'm really sorry about that. So they don't actually remove the toxic data. What they have done is they train this classifier to detect toxicity, and they say that about 0.2% of documents they have sorry, they say that they only evaluate a smaller subset, which is like 0.2% of the documents. And they say that they are assigned some toxicity score, but they don't actually remove it from their data set. And similarly, they again also do language identification, and they say that we have like these 10 languages in our data set, but I think it's not a lot. So I don't know how good of a multilingual model this Llama 2 paper is.
Shruti, can you go back to the data set once again? The previous slide, yes. So they have
Sorry, actually, I'm wrong about the toxicity part. I forgot about it. I think what they are trying to say is that 0.2% of the documents are labeled as toxic, but yeah, they don't actually remove it from.
oh, they don't removed it. Maybe they have later came to know about this, right? Okay. Higher likelihood of 0.5. Okay, and language identification, how they have done it? They have done it using fast text.
It's still online.
Hello?
So sorry, I was just taking if I'm still online or again disconnected.
I was just asking that for language identification, they use this fast text language identification tool, right? Hmm. Okay, fine. Okay, thanks.
Okay. Okay, so coming to the training details, if you look at it, they say that most of the pre-training settings from Llama 1 architecture that were adopted. For example, they use this again pre-normalization using RMS norm. They use the Swiglu activation function. They use rotary position embeddings. The only difference which they have introduced is this grouped query attention for the two larger models. We'll come to discuss that. Again, similar to Llama 1, they have used this cosine learning rate schedule and they have these warm-up steps and everything. So I think these are not very different. Regular things which we use like gradient clipping and weight decay, all those things. Okay. Now coming to this grouped multi-query attention. Okay. So what we have here is that when we have this multi-head attention, we have the same attention matrices. So if we have 8 heads, we'll have the same attention, different versions, but basically the same attention mechanism is replicated 8 times if we have 8 multi-head attentions. Okay. The issue is that this is relatively slow. Instead, if we could do something like that, so instead of having all these different matrices, maybe if we could have just one matrix which is shared among all the heads. So then in that case, this is called a multi-query attention. And if we have a grouped query, instead of say 8, we could have 4. So say 2 different heads will use the same values and the keys. So this is the only multi-query attention part which they have used. And this is only actually based on some other paper or maybe some other paper. This other paper mentions that this is actually only useful when you're training a huge model, which is basically like 65 billion or more size, or has a more size. So this new GQ is actually used only for the last 2 models, which are of 34 billion and 70 billion sizes.
Shruti, can you
Okay.
just explain it once again? What what is grouped? So what is group here?
In group, instead of having a different value and key matrix, we'll just use the same matrix for say 2 heads.
Okay.
So यहाँ पे the computation would be easy because we just have to, we can reuse the same computation for 2 heads at least.
So that means we are just sharing the weights across attention heads, right? Okay. Okay. So what they have done exactly in the implementation, how many heads was sharing the weights?
So we just have, so 2 heads will share. Oh, okay. For this paper, I actually forgot. I
Okay,
don't know. Sorry.
okay. It's fine. Maybe you can answer later. Okay, in case of multi-query, it is like all the heads are going to share the same weight matrix and the key matrix, right? Okay, ठीक है, fine.
Okay, so coming to the second aspect of Llama 2 paper. So Llama 1 was just pre-trained models. Llama 2 actually has a second type of models is RHF, which is like seconds. They also do some supervised fine-tuning or instruction tuning. And they say that actually they show that both of these components actually contribute to a better chat or a dialogue optimized model. Okay, so we'll come first to the supervised fine-tuning part. I'm sorry, I think I have missed some slide here. Okay. Okay, maybe I can just explain it using this. So for this supervised fine tuning is essentially just an instruction tuning type of data set. So what they have done is actually they say that we'll use some instruction tuned data sets from other papers. So if you look at this instruction tuning data set by Chung et al., I think I have a slide. Sorry, let me just quickly check. Okay, I think I don't have the slide here, but we have this Chung et al. Data set. It has like eight data sets which have been basically rewritten using the instruction tuning format. And I think 5 of them are used to train, and the rest 3 are used as validation set or evaluation set. And then there is this other paper, this LAMPL data set, which is by the same first author of the Llama paper. So I think the second data set is LAMPL. This is also another instruction tuning data set. We'll start with these two publicly. Interestingly, so what they say are high quality results. So they say that in their particular case, only like some 10,000s of instructions are actually very good to actually attain a good quality LLM. This is just one example where they say that if you have a prompt, then you have a response. You have a prompt and response. So this is the instruction tuning data set plus snapshot. They also collect their own instruction tuning data set, but they also utilize some other Llama and this other data set which was by Chung et al. Specific important details, but yeah, they use simple fine tuning where they have a cosine learning rate and they have mentioned that okay, this was the weight decay, batch size was 64, sequence length of 496 tokens. One important thing is that which not important but slightly more details. What they have said is that so when we are doing some sort of instruction fine tuning, what we are doing here is that we are following the same next token prediction task. And they say that we'll just zero out the loss in tokens which are already there in the user form so that we only backpropagate on the answer tokens. So this is a simple fine tuning using an instruction tuned dataset, and instruction tuned dataset is also nothing novel. It's just basically instructions and the inputs and outputs for any sort of regular task. For RLHF also, they have some details about like what dataset they have used and reward model and everything, but I'm not covering it in this particular
Acha, so
slide or
Shruti, just 1
presentation.
second. One question here. So can you go back to a previous slide here? Yes, this one. So they have trained on this only dataset, or there are other datasets also?
So these two datasets and their own curated dataset was used for instruction fine tuning. RLHF, I don't remember, and I have not added that in the slides.
No, so you were talking about the one by Chung et al. And one by Tauron et al., right? These two datasets you were talking about?
But they also curate their own dataset also for like this instruction tuning.
And is that dataset available?
I haven't actually checked that.
Can you check it and let us know?
Okay, sure.
So if that is available, we can use it for our training also. ठीक, okay.
Okay. Okay. So next we have Gemma or Gemma. I still don't know what exactly it's called. Okay, so coming to model architecture, so they say that we have just used the transformer decoder with some of the new things which were actually also used in the Llama paper. So they say that we'll use multi-query attention, we'll use rope embeddings, which is the rotary embeddings, and they use RMS norm. Okay, sorry, one thing which is not used, which is not mentioned here, but they don't use the glue activation function. If I remember it correctly, they use either JLU or GJLU, something like that. Maybe that also I can check and then let you guys know after that. Okay, so coming to the parameters. So this Gemma model is available in two sizes. We have the 2B model and the 7B model. And we have both the instruction tuned and non-instruction tuned versions. As you can see, the model dimension is 2048 and 3072. The interesting thing which you could is 16. So what they say is that we'll use the multi-query attention only for the 7B model and not for the 2B model, because this is only supposed to work well when you have a smaller model. So here they say that for the 2B model only we'll use the same key and value matrices. One important thing which you should observe here is that they use JLU TANH instead. Sorry, Ankit, what is this for? And sorry, is this a question or a information?
No, you were saying now you don't know whether they use rail or something else. It's answer for that.
So from what I remember, it's definitely not TANH. Either it's JLU or GJLU. Okay, maybe I can check the paper. and let
They
you know.
actually use this Gelu 10H approximation. In paper now, when Gelu was present, there was three formula. One was approximation using 10H, one was direct some numerical value. So this is the variant they are using actually. If I remember from architecture, not from paper, I think.
So this is mentioned here. I probably missed it. I hope my screen is visible, right?
Yes, yes, yes.
So this GJLU is the function that they have used. So this GJLU, if I remember correctly, this has a JLU component, and yeah, maybe you can check it later, or maybe I can share the exact formula later. Okay, coming back to the Presentation. Is the presentation visible or is it still on the paper?
Yes, it's
visible.
visible.
Okay, okay. Okay, so the interesting thing which I was saying is that the vocab size here, if you look at it, it's huge. We have like 256K vocab. And because the vocab size is huge, we have like a lot of embedding parameters. So if you look at it, they have mentioned these many embedding and non-embedding parameters are there. If you, sorry, okay, so they say that this vocabulary is actually reutilized from the Gemini vocabulary. So probably for the Gemini model, they say they trained some sort of sentence piece tokenizer. They mentioned that they inherited a subset of the Gemini vocabulary. So I'm assuming what they might have done is probably use some tokens and some merge rules or something, but I could not actually find the exact details of what this inheritance of vocabulary means. Maybe if I have some time, I could look into it later, or if any one of you is already aware, they could let me know. Okay, so coming to the training data. So for the 2B and 3B models, they say that we train on 3T and 6T tokens respectively. Most of this is primarily English data from web documents, mathematics, and code. And they specifically mention that this is not a state-of-the-art model for multilingual tasks or for models, for multimodal tasks. Okay, okay, there is a message. Okay. Sorry, this is the same message as earlier. Okay, so they say that we use a subset of the sentence piece tokenizer. Interestingly, they also do the same thing which Llama does, where they say that it will split digits. It won't have some sort of numbers anyway. I mean, basically the numbers will be split into individual digits. They won't have some two-digit or three-digit numbers whenever they are doing this tokenization. They again say that they do not remove white space, and they also do the same thing, that it relies on BPE, but for unknown tokens, they will again use a fallback to byte level BPE. Okay. Then for the dataset pre-processing, they say that we remove these unwanted or unsafe utterances, personal information, all these types of things. They also say that they try to remove all sort of validation or test it from the pre-training data mixtures. Now coming to the Gemma architecture, it also has again the same two stages as we had with Llama. So it will also have an instruction tuning stage, and it will also have an RLHF type of stage. So they say that again, both stages are important, and these are important for both of these stages are important for performance on downstream tasks. I won't go into the exact details of these datasets, but these datasets were actually curated by the Gemma team, or I mean, by Google only. So they have not used essentially any existing datasets. I also am not aware if they have made these available or not. Okay, so
Shruti,
coming
just
to,
one question here. So is it the case that first they will fine tune using instruction tuning and then they will do RL?
yes, sir, it's the same procedure.
Okay, not like individually, each of them. Right. So like
I
not
think
separately, I should say, right? So just one model with an instruction tune model, another one is RL tune model. So they're first actually they're kind of combining these two approaches together, right? In a sequential manner.
I don't actually remember the exact details, but I remember seeing multiple variants. So there could also be models which are just instruction tuned and not RLHF, I think. But eventually, like the one, like the final two models which we see, I don't actually remember if they have done this in sequence or. Um, but my guess is they should be done in sequential manner. Maybe at the end of the presentation, I could quickly jump to the paper and then we could check that.
Sure. Okay.
Okay, so one important thing which I thought I should maybe discuss, because it might be useful to most of us, is that we often do a lot of inferencing with Gemma models, and we often actually just pass regular input to the model. So they actually say that they have a sort of a specific formatting which they have used during instruction tuning. So the format is that they will have these special tokens, which is user and model, to denote whether it is the turn of the user who is speaking or this is a model's answer. And then you have a end of turn and start of turn type of tokens. So this basically denotes a specific conversation. So whenever maybe we are doing these sort of inferencing, we should actually sort of consider adding these special tokens, so that like whatever output that we are generating from the model, it's actually optimized because the model is trained using these tokens. Okay, so yeah, this is just some result. They say that this outperforms outperforms similar size models, which is Llama 2 and Mistral on 11 out of 18 text-based tasks. They have given these results here. I did not look into them very deeply, but yeah. I'll come to another important aspect, which is memorization evaluation. So what we often think whenever we are seeing some good performance from a language model is that it has actually already seen that thing and it's trying to memorize and basically generate the output directly from the memory. So for example, I had the same idea when I was doing some sort of question answering from LLMs, and I was thinking maybe the model has, sort of already seen the answer and it's generating the answer, not generating the answer, but trying to just fill in the next text of the token, next tokens for the question, and not actually essentially doing some reasoning and generating the answer. So this entire thing is called memorization, and they have this memorization evaluation in the Gemma paper. What they say is that they sample like 10,000 documents from each of the corpus which they have used in the training of the model, and they say that we'll use the first 50 tokens and give it as a prompt to the model. Now, if the model is able to generate the exact next 50 tokens which were there in the document, this is a test of this is basically sort of called exact memorization. So it's basically able to recall the next 50 tokens exactly. And just to add some fuzziness to this, they say that they also have this approximate memorization, where they say that if the next 50 tokens are similar but there's just a 10% edit distance threshold, this is called the approximate memorization procedure. Funnily, they have not actually evaluated other models, but they have just, if you look at this, so they have this Gemma 2B, Gemma 7B, and they have evaluated it with respect to the PaLM model. So for PaLM, this y-axis is percentage of exact memorization, and this is just English content. This is for all the content. And if you look at it, for this is actually less than 0.1%, and for the non-English content, like everything, this is somewhere around 1%. So 1% of the content is actually exactly memorized. So this basically says that the model is not essentially memorizing significantly. For the approximate memorization, so here they have these different data sets on the x-axis. So for example, code, wiki, science, web, multilingual data sets. And what you can see here is that for multilingual, this is definitely has the least amount of memorization, but even for other domains, the memorization percentage is actually less than 10%. So this is not very significant, given that this model has been trained on like 3T or 60 trillions of tokens. And yeah, this is references. Just a disclaimer, like Gemma paper had like a lot of experiments on RLHF and basically trying to say that what experiments work, which I have not covered because yeah, I was not able to understand a lot of those, and I just thought it would take a lot of time for me to finish those. So I just picked up the things which I found were more interesting. I hope I'm still online and not disconnected. Okay.
So Shruti,
Yes.
why these Gemma models are becoming very popular these days? Like if I compare with other models which have very similar sizes.
So I think I think the most popular ones are 2B models, and 2B models may we only have C2 or C3 type K models, and C is actually performing very poorly. So Gemma actually 2B actually performs very decently. Like I would say it performs, from my personal experience, it performs very good in comparison to other 2B models. Same actually I have also observed for 7B models. Like Llama 3 7B is a different game altogether, I would say. But among the existing ones like Llama 2 and Vicuna and Mistral, I think among the 7B models also Gemma is
Oh,
uh, Gemma has
so
been
it
performing
is
very
better than Llama?
nice.
It is better than Llama and Mistral?
And I think one tuning is really nice.
Your voice cut in between. Can you please repeat?
Sorry, I was just saying that the instruction following capability of the Gemma 7B model is actually very nice in comparison to Vicuna or Mistral.
Okay.
And
Actually,
I
just
also
one more.
believe that
Acha, so,
maybe
so Shruti, the fine tuning that they have done. So even though the steps are mentioned in the paper, but the data sets are available.
no, I don't think I have checked that, so I cannot answer that. Sorry, I don't know actually. I'll check and let you know.
Hmm. And what set of other models they have compared their models with? So
Because in the
Gemma 2.
paper, at least,
Mhm. Yeah, go ahead.
okay, so if you see here, on this 18 text-based stuff, they have actually compared with Llama and Mistral, and they say that so Mistral maybe have the 7B model and Llama also 7B and
Shruti,
13B,
your
and they
screen
mostly
is
say
not
that
visible.
11.
Sorry, I cannot see your screen.
Oh, okay. 1 second. Um, Sorry, I'm just trying to find the right screen. Oh, no, sorry, wait. Okay. So what we have here is that they have mostly compared with the Mistral 7B and the Llama 7B model, and they say that it actually performs better than that on say 11 out of these 18 tasks. Hello.
Yes,
I was
you're
just
audible.
looking into this. Hmm. Hmm. Okay. Hmm.
Uh, does anyone else have other questions?
Do you think due to the larger vocab size, the Gemma is performing better?
Right. So I was coming to that actually when I was discussing that. So I also do believe that, yeah, because this has a very huge vocabulary size, this is like a lot of performance improvements are maybe coming from that. But there is also this other aspect that even though they have this huge vocabulary, Gemma is not actually a multilingual model. So that is also questionable. Ideally, I mean, I would have been more convinced if this was a multilingual model and we had a huge vocabulary.
Acha, so Shruti, a lot of people are actually fine-tuning this model for other languages, right? So, what have you shown any slide where, or the paper contains any table which talks about the other languages which are there in the in the model training?
Um,
I think
so
the
for
percentage was very less, right? These were mostly Latin scripts.
Uh, so I think that was for Llama paper. Gemma may they don't have anything about like other languages per percentage.
Okay, okay. Acha, that was Llama. Okay, okay, okay.
Hmm.
So Gemma they don't have. And
Hmm.
do they claim that it is multilingual or they don't also
And
claim?
no, so they say that this is trained on primarily on English dataset. Some multilingual dataset might be there, but they say that this is not like the aim of the model is not to be a multi-model or multimodal or multilingual model.
Okay, fine. ठीक है.
And the diagram for the Gemma is same as the Llama's model diagram.
They don't have the diagram in the paper, but the architecture is same because they have used the transformer decoder, and we already saw, right? So they use RMS prop, sorry, not RMS prop, RMS norm, and then they use multi-query attention and rope embedding. So I think mostly it's the same thing as Llama 2 architecture.
So RMS norm is also in
Llama
for the
architecture,
input
yes.
of for the input of the attention layer and the feed forward layer or output.
And so that is actually not mentioned in the paper, but I'm assuming the uh, best way to do that is you apply it to all the feed forward layers and also to the the attention layer. Oh, actually, I'm
I
sorry.
was talking
I
about a
just checked the paper.
pre-normalization.
Oh, it's a
Yes, please go ahead.
pre-normalization. So sorry, I was just saying that I checked in the paper Gemma wala, and they do say they do mention that attention and feed forward layer dono में RMS norm they are using.
So
Pre-norm ka nothing has been mentioned in the paper.
okay.
Sorry. Um, well, I'll share the slides. Maybe on the Google Sheet itself. I'll just add a hyperlink there.
Okay, thanks, Shruti. I don't think there are other
Okay.
questions. So Chinmay, I will share that Google Sheet link with you.
Okay, everyone. Thank you. And bye.
Yeah, it was nice, very nice presentation. Thank you.